I think it's interesting. And again, is it robust? Well, sometimes. All right. But at least it's interesting because it's yet another idea. And in the end, if you need maybe specialized parameter choice methods, feel free to be inspired by generalized cross-validation or L-curve, or maybe this method here, because maybe you can tweak it such that it will work really nice, maybe for your problem. So again, this is based on this new method here is based on some statistical considerations, and I do think that that's the way things should go to define methods for choosing regularization parameters. All right. So let's see. The principle here is, again, let's look at the residual vector. The residual vector is nice because it's something that we have around. We can always compute it and we can look at it. And in particular, the discrepancy principle chooses a regularization parameter such that the norm of the residual satisfies a certain equation. So it doesn't use the whole residual well, it uses the norm of the residual. So out of the residual, it just squeezes one number and you look at that. And generalized cross-validation takes the norm of the residual and then divides with that trace term. So again, it's the norm of the residual. But you know, in deriving this principle here, I thought there's got to be more information available in the residual that you might as well try to take advantage of instead of just computing the norm, right? Let's see if we can squeeze more information about what's going on out of the residual. Right. So let's see. Again, let's see what happens. If we have a large regularization parameter lambda, that would correspond to a small value of our truncation parameter here in truncated SVD. That means that we have only extracted some of the information available in B, but we have not extracted all the information from B that is actually available, right? And that's because we have an over-regularized solution. On the other hand, if the Tikhonov parameter lambda is too small, corresponds to a too large truncation parameter, then we have extracted all the available SVD components that we can trust, plus some of the noisy ones. And so whatever is left is only the noisy components now in the residual, because we have extracted all the reliable stuff, only noise is left. Okay, so here, lambda too small, only noise is left. Lambda too large, there's still information in B. So we would expect the residual vector to look quite different in those two cases. If only noise is left in the residual, it should look noisy. It should look like some noise, some random. And if we're in the other situation here where information is still available, we would expect that it still looks like kind of a signal, like something more smooth, maybe with a bit of noise on top of it. So we want to track the behavior of the residual, and as we change the lambda, it should change characteristics, you know, from looking like a signal to looking like noise. Again, and we can visually do that by inspection, but we want to automate this. So we need a mathematical and computational tool to do that. And in fact, the statistical question we need to ask is, or that we can ask, is my residual vector, can we consider that a noisy signal? Yes or no? Okay. And statisticians can help us answer such a question. And a tool for doing that is what the statisticians call the normalized cumulative periodogram, Ncp. Okay. So what is that? So we define, so what the statisticians call a periodogram, that's what signal processing people know as a power spectrum. It's the same thing. It's just two different communities come up with two different words for the same thing, right? So the power spectrum is, I'm an electrical engineer, so I like to call it a power spectrum. So the power spectrum of the residual, well, you compute the residual and you compute the discrete Fourier transform of that. That's a vector. You square the elements of that, and that's your power spectrum, right? With indices going up to n-half. So that's the P. And then we compute a cumulative periodogram. Okay, so that means that we sum the elements in the periodogram. We compute a vector. The first element in that vector is just the first element in the power spectrum. The second element in that vector is the sum of the first and the second element in the power spectrum. The third element in that vector is the sum of the first and the second and the third element in the power spectrum, and so on and so forth. So you see, that's what we've got here. And instead of writing a sum, I just write a 1 norm, because that's the same thing. All these elements are positive, so it's equivalent to a 1 norm. And then you see, damn it, I don't start in the first element. I actually start in the second element. And so I have to go to k plus 1. That's because the first element in the power spectrum is the electrical engineers call the DC component. It's the something associated just with a mean value. And that's not important for this analysis here. So we throw that one away. So that's what we start with element number 2, which is like the first harmonic of the signal. Right, so that's what we mean by cumulative periodogram. We got that now, but it's normalized. So we divide by the 1 norm of the power spectrum, the sum of all the elements there, except for the DC component. So that's the Ncp. It's a vector with n-half minus 1 elements, minus 1 because we threw away the DC component. So that's a vector now. What does it look like? Well, you see, okay, if the residual, if this vector sitting there and there is actually pure white noise, then what would that vector there look like? What characterizes white noise? It characterizes that every spectral component has the same expected value. So if you plot the power spectrum, it's supposed to be flat. So an equal amount of all frequencies. I think that's also why we call it white noise. It's similar to white light, which has all the visible frequencies available. So anyway, a white noise signal has a flat power spectrum. So all these elements in this guy here, the expected values of these guys will be the same value. So of course, when we add them, we're just going to have a vector here that steadily increases. And when we plot it, it'll be a straight line. I hope you're with me right there. And sure enough, of course, when we plot this Ncp vector here for realizations of white noise, we're not going to get a straight line because it's only on the average we expect a straight line. But what you see here are 10 different realizations of white noise. And you see that these vectors, they actually wobble up and down a little bit, clearly around a straight line going from 0 to 1 And this is the number of, basically the number of components that we're dealing with in the vector. So of course it starts around 1, because that's where we have only one component in the sum here. And it ends up here in 1, and that's because when we have the largest value of k, then the norm here and the norm here in the numerator and the denominator are the same, so it should end up in a 1 over here. So sure enough, white noise actually gives us some curves there that close to the straight line in between here. So that's very nice. So if we see that kind of behavior there, it's probably true that the signal is white noise. And in fact, statisticians can tell us much more. For example, we can introduce something called the Kolmogorov-Smirnov limits. They are defined right here at the bottom. And they define like an interval around the straight line in the middle. And the statistician will then say that with a 5% significance level, then the noise is, we can accept the noise as being white if it lies within those bounds here. And that seems to be true for all these guys here. Well, maybe the green one here is right at the border, I don't know. But all right. So that's what we can do. Another thing, so the Ncp vector here, if that is kind of like a straight line, it's because the residual is white. Just to see what happens when it's not white, let's try to look at these Ncp vectors for the case where the residual is dominated by low frequency noise and high frequency noise. So in the plot here in the middle, well, this is what happens to those curves when we have low frequency noise. I think that's sometimes called pink noise. And then we see these curves, they increase rapidly, go way outside the Kolmogorov-Smirnov limits there, and then they come back because they all have to end up in that point there at 1, of course. And so why is it that they increase fast in the beginning? That's because there are a lot of low frequency noise, right? So there are lots of contributions to the spectrum in the low frequency end, and in the high frequency end, not very much is added. So it has to bend that way around. And then, of course, for the high frequency noise, what is that called in signal processing? Is it blue noise? I'm not sure what it is. It's not pink. Let's say it's blue. The curve bends the other way because there the main contributions to the spectrum comes from the high frequency components. So that would be over here towards the end of the curve. So clearly, if the noise is not white, it looks different than the straight line. So that's very interesting because, you know, if we back up a little bit here to the previous slide, that's exactly what the question we ask is, when do we reach a lambda regularization parameter where the residual starts to look like noise? Right? So when do we reach a situation where the residual starts to look like something like the white noise there, of course assuming that we have white noise in the data, otherwise this is not going to work. All right. So back to regularization test problem here, where we compute Tikhonov solutions for various values of the regularization. You can see different values of lambda here along the axis here, and what we have along here are the components now in the Ncp vector. And you can see, and then every Ncp is shown as one of these blue curves here in this 3D plot. I plotted it this way because I wanted you to see the transition of the Ncp curve as we change the regularization parameter. Now let's see. up in this end here, when lambda is larger, that means that we over-regularize, we extract too few SVD components from the right-hand side. So that means that the residual still carries information. It still carries some signal that we have not yet extracted. And the signal is dominated by contributions from larger singular values, and we know from the first lectures that will be low-frequency information. And sure enough, the Ncp curve has that form that it increases rapidly, and then it becomes flat, indicating that it's certainly not white noise. It's dominated by low-frequency information. So as we decrease lambda, when lambda becomes smaller and smaller, we include more and more SVD components into the solution, and sure enough, the Ncp curve starts to change its behavior. You can see that. Hopefully you can see that. Right. And then at some point here, lambda is really quite small right there. And that means that now we include a lot of the noise components also in the regularized solution. And certainly at that stage, the residual is dominated by some high-frequency noise components. And you see now the Ncp curve is bending the other way. Right. And in between, there is a value of lambda for which the Ncp curve is pretty much almost a straight line from one corner to the other one. And that might be this particular line I'm pointing at right here in the middle. So according to this principle here, this is exactly when we have extracted all the signal, and what is left in the residual is something that resembles white noise. So we're getting closer now to having a method here. We should adjust lambda until we get a curve here that looks as much as possible like a straight line. And that's the Ncp criterion, really, using this normalized cumulative periodogram. So what you do is you compute your Ncp vector, you subtract it from this vector here, that's the white noise line, that's just a straight line, right, going from one corner to the other. You subtract those, and you can, for example, compute a norm of the difference, and then you minimize that deviation from the straight line there. And then you have your method there. That's the Ncp criterion. And this is what is implemented in regularization tools. So, yet another method, the Ncp criteria. There's a basic assumption here that the noise in the data is actually white noise. And when we teach this stuff here, and when we're doing exercises, we really like white noise because it's easy to generate and it's easy to understand. I think in practice, very often the noise is not really white. And then what to do? Well, sometimes we may be able to estimate the covariance matrix for the noise. And then, of course, signal processing people know how to actually work with the inverse of the covariance matrix, apply that to the data in order to transform the data into a new type of data that has white noise. It's called pre-whitening in signal processing, and maybe some of you are already familiar with that. So that's a nice idea. And if we cannot do that, then I guess it's up to researchers to try to come up with different versions of the Ncp criterion for noise that is not white. There's definitely some interesting work to do there. Anyway, in this course here, we'll just be working with white noise. So we would expect that at least sometimes the Ncp criterion here should work. Okay, so here are the four methods that I have covered today. I spent a long time actually today on this. Discrepancy principle, L-curve, GCV, Ncp criterion. And man, time is running. I I wanted also to discuss the robustness of these methods here. Now I'm eating of the time that where you're supposed to do exercises. I hope you can bear with me. I'll use like 5 or 10 minutes just on this stuff here because I think it's important. So what we compute here is essentially we compare the regularization parameters computed by these 4 methods here. And we compare it with the optimal regularization parameter. The optimal regularization parameter is that gives the parameter that gives the best Tikhonov, the solution, the one is the closest to the exact one. This, of course, you can only do for Mickey Mouse problems where you know the exact solution. But in this way, we can evaluate the performance of our 4 parameter choice methods. So here's one example here, and I'm showing histograms of these ratios here between the parameter chosen by the particular method and the optimal one. And of course, you'd like these ratios to be, all of them should be ideally equal to 1, because that means in every experiment you've just found the right regularization parameter. And then these histograms here tell us what's really going on here. And okay. Why don't we start with something nice? The Ncp criterion that we have here in the bottom right corner there, where you see that really the mean of the behavior here is really at 1. That means that in most of the cases we compute a regularization parameter that's pretty close to the ideal one. And then there's a bit of a tail here where the regularization parameter is too small. Right, so Ncp seems to work very nice for this particular test problem. Here's GCV. GCV tends to produce a regularization parameter that's a bit too small, but that's not too bad. Then we have the L-curve criterion. And depending on the noise level, this might work really nice or really not so nice. With a very low noise, it doesn't work so well because it consistently gives a much too small regularization parameter right there. And then finally, discrepancy principle. Again, most of the time it works very nice, and then again there's some tail right there. Here's another test problem there. Why don't you take a look at that one there in the book if you want to see more examples. So let me just finish up here. So going through these methods here, discrepancy principle is a very simple method. It's easy to implement, but we must have a good estimate of the noise. All the other 3 methods do not need an estimate of the noise level. There's the L-curve criterion here that we can automate if we can compute that curvature. There's based on pretty much a heuristic. There's a GCV criterion, which is based on solid statistics. Also very robust, very nice method. And it may fail once in a while, but typically when it fails, we definitely know it has failed. And then the most recent method in this category here is the Ncp Criterion. That so far only works for white noise data, but it can also be successful once in a while. Okay, and you'll look at these in your exercises, so let's stop here. Right.